Fabio Riccioni from IFN Rome and Sapienza. He's going to tell us about the multipolar structure of Myers-Squiggly consents contouring up. Please take it away.
Okay, thank you, Carlo. So let me first of all join all the other speakers of this group by thanking the organizer of the conference and for arranging the conference, also for inviting me to give this talk. So this is indeed the title of the talk, multipolar structure of Myers-Squiggly black holes. So this will be some sort of really, I would say, off topic compared to the other talk, most of the talks that have been given during the week. But there will be, Riccardo made some anticipation somehow, and also mentioned a little bit what the problems that arise when one starts going in to higher dimensions. So I will refer to actually to the things that Riccardo mentioned. So indeed, I mean, many things happen, as we know, in dimensional area 4. So there is no. So from the gravitational point of view, there is we know for the matter there is no hair here, and so curved black holes are basically, let's say, Newman black holes are basically unique. Many more different things can happen in dimensional area 4, and there is analogous statement from in the amplitude language of this unicity for languages. So many things a few things came out during Riccardo's talk. For instance, the issue of simplicity. The issue of simplicity. Well, we'll mention this during the talk, but indeed, I mean, this is one of the things that we simply are not, I would say, even not well defined in dimension in order for dimension. So let me start with so we will be talking about multiples in gravity. So let me start with a very simple introduction on gravitational multiples in 4 dimensions. And this is basically a quick review of the work of Kip Thorne back in 1980. What is the idea? The idea is you study stationary asymptotically flat vacuum spacetimes, so you just expand G mu nu as eta mu nu plus kappa H mu nu, and you want to study first of all the EG. The vacuum Einstein equation. So there is a simple trick, which is to move from H, define what's called the trace reverse perturbation gamma mu nu, which is defined as well, should take H mu nu minus K over 2 eta mu nu times the trace of H. And this object is very convenient because the Einstein equation for H becomes simply box gamma mu nu equals 0. And the Donder gauge, so the harmonic gauge, if you want, becomes for H becomes simply the Lorentz gauge for gamma. So if you if you solve this equation, you simply solve it in terms of sum of harmonic functions. So basically, we are in a static, so it's a stationary regime. So nothing, the metric doesn't depend on time. So we can write gamma 0, 0 simply as the sum over from 0 to from L equals 0 to infinity of some coefficients, some tensor m, which we calls MAL, DAL 1 over R. I'm going to explain what is notation here. Gamma 0 I, similarly, sum over L equals 0 to infinity of J I AL D AL 1 over R, and gamma IJ is the same as sum over from L equals from 0 to infinity of Gij AL, so this is an A, DAL 1 over R. So what is AL? AL is just a set of L symmetric space indices, but on top of this there is, of course, 1 over R is harmonic, so any trace in any trace part of M disappears. So this is basically AL, the set of AL indices are what's using the notation of Krypton, what's called symmetric trace free. Okay, so of course here there's lots of reducible, well here at least there are reducible representations, but on top of this we have to impose the gauge.
Sorry, can you?
Yeah.
This AL is their spatial indices.
So this is special. So, but let me write for once and for all. So this is basically, I mean, with this I mean M A1, AL, DA1, AL. But sorry, this is an L. But the trace here, box on this is identical zero. So you have to keep.
So sorry, the trace plus combination.
So this is a trace combination of this symmetric. So this trace is symmetric. So this is what STF means.
And AL go from 1 to 3.
Sorry? Yeah, we have four dimensions. Yeah, we suppose the three space dimensions. Yes. So this will be, so all derivatives of 1 over R, I mean, which are minus the trace, we can principally clear. But the point is, once you impose the gauge, you realize that only, actually, this function, this tensor, and one particular combination, one particular representation of this tensor survive. So the only remaining, after you fix the gauge, the only remaining, we say, multiples are MAL, let me call it STF, that was already STF, BAL, 1 over R, and well, you can write down this combination, which is some. Well, the point is, in three space dimensions, you have epsilon 3 that you can use, and so you can extract an epsilon I, say A1, A2, and then you have a J, A1, A2, A, say L minus 1, L minus, sorry, say J A1, A L minus 1, STF, DA1, DAL. And gamma ij, you can just simply put it in 0. So there are only two sets of multiples are left appear, which are what people in GR language are called the mass multiples, which is just a set of M, let's say M A L STF. And the current multiples, which are the J, A, L, STF.
So if I just make sure I understand, I guess one of the lowercase A1 should be an A2, right? In, I
So
J.
this is an A2, yeah, indeed. So the point is, out of all the possible, all the representation, this representation is because of epsilon zero is STF. Okay, this analysis, to an extent, this analysis in all the parameters in G, and so actually what happens is that you have a sort of gauge, you have a way of defining these tensors in a sort of gauge invariant way within a set of coordinate transformations that are a set of coordinates that are called ACMC, asymptotic Cartesian mass center coordinates. So within this set of coordinates, this definition of multiples is gauge invariant. So if you go from one ACMC set of coordinates to another, this doesn't change the multiples. And so we are in vacuum, and for instance, one example of these coordinates are the harmonic coordinates. So harmonic gauge is an ACMC gauge. So if you, for instance, take care in your favorite, say, polyaliquid coordinates, these coordinates, so and you try and expand in G this the metric in these coordinates, and you read the multiples from there, you're going to fail simply because the polyaliquid coordinates are not ACMC coordinates. So you can't read the multiples of K directly from the polyaliquid metric. So okay, this was the
Sorry,
So just to check if I understood, so it's a set of coordinates which guarantees that the multiples are gauge invariant, or is a set of, or within this family of coordinates?
It's a set of coordinates such that you can define the multiples, and the multiples are invariant by if you go from one set of coordinates to the other.
But within this ACMC set of
Within this
Ah,
set of coordinates. So as I said, you can't go to Boyer linkers because you will fail to read from there. But the point is, this set of coordinates is such that any correction will be higher order, so in 1 over R compared to the leading terms for each multiple. So this is the idea. Good. So this is basically our. So this is put this like as a motivation, and basically what we want to do is. So let me stress now the philosophy of this work. So the idea is we are motivated by scattering amplitudes techniques, and as Riccardo also anticipated, in the framework of scattering amplitudes, you're used to thinking of the energy momentum tensor in, say, momentum space. And what happens is that, as Riccardo was mentioning, the energy momentum tensor of we can think of in the context of scattering amplitudes as a curve being generated by an energy momentum tensor, which will be sort of for instance, for Schwarzschild, it's clearly the delta function of the source. In momentum space, this will become something which is the object that you read from scattering amplitudes. And the idea is to relate basically the energy momentum tensor that you construct in momentum space from scattering amplitudes, relate this object to the multiples that occur here. So this is the philosophy. So let me formalize this a bit better. So this is the idea we have in mind. In scattering amplitudes, the idea is to construct the energy momentum tensor for a 3-point amplitude as before. So we have an object of spin S with momentum P1 and polarization epsilon 1. And an object of, I don't know if you can read P2 epsilon 2. You have transfer momentum Q, which is P1 minus P2. And from this amplitude, you simply read the energy momentum tensor. And the idea is to use this momentum tensor as a source for your metric. And basically, you can write down the metric if you know X. Of course, everything is static here. So we are considering only static configuration. So sorry, I mean solutions, the metric that don't depend on time. So you get something like integral on 3qx, 3 on 3q of 2 pi. To the minus I q dot x over q squared, then it will be your propagator projector, which you call p mu tau sigma of q. So let me stress it again. So what happens is from this amplitude you compute you just get an energy momentum tensor. If you put this energy momentum tensor inside as a source at first order in G for your metric, this is what you're gonna read. Here basically I'm using, so this is So this is the propagator in typically in harmonic age. So this is the idea, and so we want to compute P mu of Q. So we want to write down. So, but the idea is to sort of to have an understanding of the general expression of an object like this, of what can be an energy momentum tensor, the energy momentum tensor in momentum space. And there are some rules that come from that we can simply read from this formula. I mean, in general, from the scattering up results. So the rules are, first of all, that we neglect q squared terms, and And this is obvious if you look at this formula. I mean, q squared times in t will simply cancel this denominator, and simply in this integral we will get something which is a delta function of derivatives of delta function. So these terms are what people call local terms. And so you neglect these terms, which will give you not increase, not classical result for H. The other rule is you neglect terms of the form they contain q mu, and the reason is and also proportional to eta mu. And there are two ways of seeing this. One is, of course, from the point of view of scattering amplitudes, because if you think here, if you contract here with your graviton property, your graviton polarization epsilon mu, these terms will just disappear. This will be cancelled contracted with the polarization of the graviton. But if you look at this formula, these terms will produce in H terms which are we find out that these terms will produce in H terms which are can be gauged away by gauge transformations which are within the gauge. So you basically can, so for instance you choose your favorite gauge like harmonic gauge, you have still gauge transformation within the gauge, but these transformations allow you to neglect all the terms that arise here from terms in the mu of this form. Good. So there are the rules, of course. The other rules. The other rule is so. Let me write. So we will. So we want to. The point is now we want to write down the homogeneous expression of t as an expansion in momentum in q and the spin of A. So we want to write down the most general object that is spin induced by a source that only has whose multiples are only functions of the spin. And the spin is is some object. Well, I define Sij as the spin density. So this will be a matrix. So if an object rotates along the z-axis, this will be something like this. But A, for instance, for care, this is A is the A of care. So this is actually the J angular momentum divided by mass. So indeed, as we think of S as being spatial terms, it's ordinary spatial indices. And for the other conditions that I have is that the other condition which we know from which we apply all the time in this scattering amplitude analysis is I would call the H bar rule. That basically when H bar goes to 0, Q should scale like H bar Q, and S has 1 over H bar S. So basically, times Q powers of Q dot S, Q contracting with S, powers of Q times S in general, to any so Q times S to any power will be a classical object. So what we write down is an expansion in Q times S.
So what about terms that are like S square?
Terms that are S square, but then this well, you have to eventually have to compensate with Q. So there's a dimensional. So what you
well, in principle, you could have Casimirs of the spin that when you want to interpret as a classical. So if you evaluate for spin equal 1, it's just a number, but you want to keep them because then you want to think about classical spin. So I think it's a bit of a delicate point, right, when you want to do spin.
Yeah, typically this time you don't include. Let me give an argument. Well, okay. How do I see in the symbol terms?
Well, I think you do include it, right? Because you include things like q dot s dot s dot q, but
that
also
will be the general
but also s square q square.
Well,
because
q
of
square
that
is q square.
That's what we are saying, because s square is the Casimir.
But q square you're not allowed to include. So q square will give you no classical.
If it's multiplied by s square.
Yeah, but it will cancel the 1 over q square.
Okay.
Any Q square,
Right,
of Q or
okay.
S, any term which is simply Q mu, Q square in the sense of
All right, because you're using this formula. Fine, yeah, because you're looking at this 3 points. Yeah.
So you choose all these terms.
Yeah.
So the so the most general. So let me write down the most general object we can write down. And this is
Okay.
Q. So it will be okay. Let me define two quantities. One is we define E mu simply that which is delta with 0, because we are in the frame in which our object is sitting at the origin. This sort of the static frame, and another object which we define is zeta square, which is minus q dot s dot q, and which is what Carolina was mentioning. This object, if you work it out, so this is s. This is simply a square q orthogonal square. So this is a square qx square qx square plus qy square. Good. So let me write down the energy momentum plan. So this will be m. This would be an infinite set of terms which are proportional to mu, and these are because this. So this will be some energy plan from 0 to infinity of f to n. Let me call it the 1 zeta to the n. Then you have a term which is minus I m over 2 u mu s dot q mu plus u mu s dot q mu times sum of f to n plus 1 3 zeta square, zeta to the n. Some from n to infinity. And in principle, you can write another term which is plus sum of plus m sum of from n from 0 to infinity of f to n, we call it 2n plus 2 with an index 2 with a subindex 2 s dot q mu. S dot q mu, but it would be outside the sum, zeta to the n. So zeta to the so zeta square zeta to the n. Okay, now there's something magical that happens in exactly 4 dimensions, and this, as we will see, is exactly the momentum space analogous of this statement here. Is the fact that in 4 dimensions you can fully gauge away this term here. And the observation is the following: if you take this term s dot q mu, s dot q mu, you can do this. You can do this as an exercise. Take this term here. You can show that this term is actually equal to mu and times zeta square, up to terms which are of this form. So basically, this object is just a redefinition of this object. So we just ignore it. So this sum you shouldn't look at it. You shouldn't consider it. So all the terms that contribute to h that come from this term are exactly equivalent to this term. So just with this, include this term, it will be just a redefinition of this confusion. Okay. Okay, so now you plug this into your, you plug this into the definition of the relation between T and H, and you use this relation, and so you plug this into the relation, the relation with the H, as I said, and you read the multiples as functions of f. And what you realize is that the MA to L is proportional to f to L1 times, well, let me, it's convenient to work out, to write down Sij as epsilon ijk, that's k, of course, in three dimensions, but as we know what it is. And so this will be simply S say 12, a tensor which is S1, S2L, completely symmetric and trace-free. And again, J, A, 12 plus 1, so this is will be, so there will be only even indices, only even powers of S, powers, or even, yes, powers of S here, and odd powers of S here. So this will be F 12 plus 1, 3, S 12 plus 1, 3 is 3. So this is basically A to the 2L, and this is A to the 12 plus 1.
So compared to before, there was symmetry trace-free before.
Yeah, but now this object has only one index.
Exactly,
So,
yeah,
so
yeah.
for a spin object, if
yeah.
for dimensions, this is like one
Honestly,
index.
okay.
And in order to do the comparison, you have to perform a gauge transformation, no? Because
No, well, the relation, so when you write down h mu of x as the integral of 1 or 2 square p mu rho sigma tau rho sigma of q, this object is the projector in a specific gauge you are considering. So this object will tell.
it's not just eta mu rho, eta mu sigma.
This is really for instance, in the London gauge, this is with the projector on the particular gauge. So it's usually in gauge invariant theories.
So it depends on Q.
Well, this depends on Q.
No, but P.
This is just there.
Capital
This
P.
is just a project. No, this is where you can make it. Well, it can depend on Q. Typically, does not. In the dome, that does not depend on Q.
Yeah,
It's
yeah,
just something.
that's what I have in mind. In that, but if you choose that, then H mu would not be in the transverse traceless gauge where these formulas on the blackboard apply.
It is. Harmonic gauge is a CMC gauge. Sorry.
Maybe a terminology issue, maybe. You don't
This in the Donner gauge.
when you just plug over there eta mu rho, eta mu sigma, etc., the resulting thing does not satisfy d dot equal to 0, right? The condition that you impose on gamma
D-
mu.
It does. At first order in G, it does. I mean, it's really the Donner gauge. That's the Donner gauge in this.
But beyond the first order in G?
Okay, this is a whole more complicated story. I mean, for beyond first order in G, what you do is to start to include the loop amplitudes in this construction, basically. So what happens is we start to consider loop amplitudes, so the energy moment test will be modified all the power in G by the terms of gravitons self-interacting, and this you feed into this equation order by order in G. So you get
Yeah,
an
but I'm
energy,
still confused
so
as
basically
well.
you get an energy moment.
Yeah.
So do something like this. You get an energy momentum tensor at each loop order here. So for each loop you get a post-Minkowskian correction to this expression. So you get a Tn minus 1,
But the P mu
which you put here to get the order H post.
yeah, but of the external gravity propagator, you always use the P mu in terms of eta.
Yes.
Okay.
Yes.
Okay.
So you solve this order by order. So this is M minus 1. So in principle, I mean, I'm doing the 3-level analysis, but I mean this is completely general. Okay, so can I have questions? So now what happens for care indeed? Well, for care we simply have to, well, I mean this is all actually known. But what you have to do is, for instance, if you have care in Boyer liquids, you just have to move to harmonic coordinates. So there is a prescription to do this. So harmonic coordinates satisfy G mu, the mu of the coordinates, which we call, let's say, T x, y, z equal to 0. So you define x, y, and z, but actually t is the same as Euclid's. You define x and y, z as functions of the original Euclid's coordinates to solve this equation, and you get your harmonic coordinates order by order in G, and well, I mean, you can do it numerically order by, so you can fix your, say, you want to do this at order n in the spin, at a given order in the spin expansion, a given order in the Poisson-Minkowskian expansion, and you get your metric and you get your coefficients. And what you find is that F2L 1 is equal to minus 1 over L, minus 1 to the L times 2L over 12 factorial, and F12 plus 1, 3 is equal to minus 1 to the L times 12 plus 1 factorial, which means that T mu nu is simply equal to M u nu cosine of zeta minus I m over u mu s dot q mu plus u mu s dot q mu times sine zeta over zeta, which is probably something. Well, this is so. This gives you. This is the energy momentum tensor of. So what is this? This is the energy momentum tensor of Kerr in momentum space. Let me. Probably I can just sketch how the same construction at that given order that was in the spin expansion. Of course, if we actually do an actual amplitude computation. Which is probably worth doing. So suppose I want to study this process with I just erased this process here for a spin 1 field. So I have a massive spin 1 field that is minimally coupled in the sense of Lagrangian, which is minus which is minus 1 quarter f mu f mu plus m square over 2 mu, so I say Broca field. And I couple this to gravity, and I simply study this amplitude. And I read the energy momentum tensor, and this is going to be 1 over m epsilon of p1 dot p2 p1 mu epsilon star of p2 mu plus epsilon, but the one to exchange, so epsilon p2 dot p1 mu epsilon p1 mu symmetrized minus epsilon star of p2 dot epsilon p1 mu p2 mu, where p1 and p2 are the momenta, the moment of the so incoming outgoing moment. Okay, so this is what I read from this amplitude, and now what to do is to read from this amplitude where the spin dependence. So how does this work? How do I extract from here how this object depends on the spin? First of all, we do that. So we define first of all P as P1 plus P2 over M over 2, and the transfer momentum Q is P1 minus P2. So in this sense, P1 will simply be E. So we are in the frame which we write P1 as E Q over 2, and P2 is E minus Q over 2. And E is basically, well, say M plus Q squared correction. So basically, up to Q squared correction, E is basically M. So how do I define, say, the spin operator here? The point is that these polarizations here depend on the on the, so are boosted compared to a static object. The particle 1 is boosted by with momentum q over 2, and the particle 2 is boosted by momentum minus q over 2. So what I simply have to do is I define the spin density Sij as proportional to say this combination at in the frame in which this object is standing. So P, I take the polarization of the particle 1 and I boost it back to P equal to zero momentum, zero space momentum, and I get I call this polarization. This is the polarization epsilon 1. And similarly, I do the same for the particle 2, so I boost it back to so what I'm doing is to write these objects as this polarization times a boost. So simply, if I generally boost k, epsilon 0 of k is k dot epsilon 0, because this is the polarization for static vector. Static objects of Turing spatial over M, and epsilon of k is equal to epsilon 0 plus k times the scalar product k of epsilon 0 divided by 2n squared. This is exact up to, well, I think k here can be either q over 2 or minus q over 2. But the important point is this definition here is exact up to up to corrections in q squared. So if I plug this in here, I fail to read the exact amplitude for terms which are q squared. So for terms that I am not interested in. So in this sense, as far as the classical limit is concerned, these expansions are exact. And once I have this object, the point is I build the spin operator out objects with spin 1. So there are only two objects that I can construct here, which is the antisymmetric combination, which is basically the generator itself. But then, of course, I can construct the symmetric combination, which is SIK, SKJ, which is symmetric in IJ. And this will be related, well, I will read it from here. This is related to epsilon I 1 p equals 0, p0 equals 0, epsilon j, epsilon 2 versus property star here. Epsilon 2 star j symmetric. So this is the strategy. I simply expand the polarizations from the rest frame. So I write down this object as in terms of this expansion. I use these expansions here in terms of the polarizations rest. And whatever remains, I read the possible operators I will construct, which are basically symmetric or antisymmetric combinations of epsilon. Of course, there's nothing else I can have. I mean, these are just two objects of spin 1. I can only construct a singlet, an antisymmetric combination, and a symmetric combination, which simply means that this amplitude can only contain a monopole, a dipole, which is the first order in S, and a quadrupole, this is quadratic order in S. And indeed, if I simply do this and I work out this expression, what I find out is that T mu nu is simply equal to M u mu 1 minus 1/2 zeta square. Remember, zeta square is a term, zeta square is a term quadratic in the spin. And then there is a term which is simply minus I m over 2 u mu s to q mu plus u mu s to q mu. And if you look at this, you get exactly this expansion up to the second order in zeta square, in zeta square, which is this term here. What this means that this particle, this amplitude is mimicking Kerr up to exactly it just gives you the exactly the right multiples up to the level of the quadrupole. Suppose I wanted something different from Kerr. If I want something different from Kerr, I simply should include something which is which goes beyond, say, this minimal clapping expansion, which will be a term of the form, for instance, alpha, a mu nu rho sigma, f mu nu f rho sigma. So if I include this coupling here, so this higher derivative coupling here, what I find out is that this is actually the only term that can give a classical contribution. The only classical contribution can give is to modify the quadruple term, because I can't modify the diagonal term because this is uniquely defined. And so the only term that is and actually I can change here is the coefficient of the zeta squared term. So this will give you a different coefficient for the zeta squared, and this will be something which is not care. So for instance, if you back in the 60s, after a Thorn in probably 68, showed how they wrote down the metric, which is exact in G, quadruple order for a spinning two object. So any object any object whose multiples are functions of are only functions of the spin at quadruple order are exactly contained in these solutions. And exactly you can match a quadruple order we did it at some orders, a few orders in G, but a quadratic order we managed to reproduce the orthogonal expansions, including this. So what's happening is this is completely general in 4 dimensions, because if you think, for instance, so what we are saying here is simply that if you want in group theory language, we're saying simply that 3 times 3 is equal to 1 plus 3 plus 5. Where this is the monopole, this is the dipole, and this is the quadrupole. So we are simply saying that this object with epsilon I and epsilon j can only construct these different multiples. And of course, people in the spin analyticity community found out that there's something magic happening actually. That in 4 dimensions, there's the fact that if I consider minimally coupled spin S times S will be something like 2S plus 2S minus 1 and so on, up to the singlet. So for an object with spin S, I can reproduce the multiples up to 2 powers of the 2S power of the angular momentum. And all these objects have exactly the right coefficient for K. If I take what they call the minimally coupled interaction. So this is where the simplest in probably also the Gauss law comes out. So what simplest matrix what is simplest matrix simply the 3-point function which has the behave the best under in the high energy. So basically it has the lowest powers. The highest power of the mass. And this corresponds from the point of view of this Lagrangian perspective to minimal coupling. So this is why our minimally coupled theory exactly reproduces K. And we actually did as an exercise a spin 3 half case for fun, and you exactly realize if you take purely massive radar swing, you get exactly the octuple of K. So what happens in 9 dimensions? In 9 dimensions, the situation is simply all things become more complicated, and the first thing that becomes more complicated is really the multiple structure. So I'll focus up simply on T plus 5, but the analysis is completely general. So what happens if I try and repeat the Thorn analysis in dimensional area 4, I found that element 0, so for the mass multiples, the picture is the same. I got this standard SDF tensor. So for instance, 5 dimensions, it will be 1 over a square. So this is a symmetric object, traceless symmetric object. If I consider gamma 0I, this will be a tensor GI AL in a representation which we call, well, sorry, antisymmetric, trace-free, I mean antisymmetric, and so basically this is the reducible representation of SON of this form. And finally, gamma 0I is no longer, gamma ij, sorry, is no longer 0, but this is gij. There will be a representation that survives, which is which is this representation, which we call RSTF. So where R stands for Riemann, because in the case of because it is the representation here, which in the case of the quadruple is simply the Young tableau of it's a real representation of the Riemann tensor. So again, in the case of the quadruple in dual 5, we get this. We have this multiple here. So M is this object here, which is the representation of 3, 3. Remember, SO4 is isomorphic to SU2 times SU2. So I label the representations in terms of the two representations of SU2. J is this representation here, which is actually reducible, it's 3, 1 plus 1, 3. And this object, G, is this representation here, which is 5, 1 plus 1, 5. I do exactly, then I try and do exactly the same analysis as before. I write down the most general energy momentum tensor according to the same rules. And what I find out is that now the term sum of for n equals from 0 to infinity of S dot Q mu, S dot Q mu, F to L plus 2, 3 zeta to the 2n. This term here is no longer equivalent to the other term in the energy momentum tensor. So this is going to be a new term that arises in the energy momentum tensor. And indeed, these multiples are proportional to these coefficients in this way. So the mass multiple MAL will be proportional to, if you do the analysis, to F2L1 plus 2 twice F2L, sorry, F2L2. No, this is not, oh, sorry, this is 2. 3 was the other one, so times F2L1, let's see, S dot S to AL, so pop out AL products of S in the symmetric case. But now this is a tensor, no longer. So this means the notation here means this is S dot S A1 A2 S dot S A3 A4 completely symmetrized. Again, J I A so this is 2L. This is symmetric. These are the odd number of the current multiples have an odd number of indices, and this will be F2L plus 1 3 SI A1 S dot S A2L. Sorry, I'm missing one index. Yeah, this is 2L. No, this is 2L plus 1. So this is 12, A12, and this is ASTF. And finally, the GIJ A12 will be proportional to this, simply to this term here, F12 to SI A1 SJ A2 S dot S A12 minus 2 RSTF.
Can you remind again ASTF and RSTF?
ASTF is simply this. ASTF means projecting on this representation, and RSTF means projecting on this representation. So so this is the.
I see.
So this is a specific irreducible representation.
I see.
So in terms, if you now, so basically on 5 dimensions, so Sij will be a tensor. You can parameterize at 0. You can choose a basis in which your tensor has this form, as we know from. For those of us familiar with, for instance, with Myers-Berry. So you have two angular momenta now, because you have four spatial directions that are rotating independently on two planes and the other two planes. So what happens is that this object, if you take, for instance, so this object will be proportional to a square minus b square. This object to the a power n, probably L probably. This object will be proportional to a times a square minus b square to the L. And this will be proportional to ab a square minus b square to the L. So there are some a few interesting things you can see, for instance. You can have, for instance, in the case, you can have, if one of the two angular momenta is 0, this term is not present. So everything is expressed only in terms of the mass variable. But of course, you can have the opposite situation in which A is equal to B. This is what people call the cohomogeneity one limit, in which something special happens in Myers-Berry. Basically, the fact that the metric the official is one cohomogeneity one, so it depends only on one coordinate. The metric depends only on one coordinate in a specific coordinate. What happens in this case is that this term vanishes, but for the quadruple, so there is a term AB. Okay, this is really not the multiple. So if here there is a term AB, that's right. So there is a quadruple, non-vanishing quadruple field, which is basically well, if A is equal to this. So we call this object a stress tensor. So we call G we call it the stress multiple. Simply because, for the obvious reason, that are related to deformations of that special part of this gamma net.
So this is the only term that survives at all a disorder, or
This is the only multiple that's well. You have a dipole and this form of this part. In this, you're talking about this limit.
yeah, A will be.
In A equal B, there is only a dipole A.
When L equal B.
Well, this term is not. Sorry, this is confused. This is not L. There's not the
Yeah.
power of the movement. It's just some
from
power.
0, yeah.
So if at the level of the dipole, you simply have A. So one of there is a dipole term, but it's always a double term.
Yes.
And then there is this particular type quadruple term, and all the rest vanishes. Yeah. All the mass multiples vanish.
But shouldn't you, maybe I'm confused about like what the result of the computation will be in terms, for example, of the metric, but shouldn't you somehow reproduce the square roots that you get in the metric?
Square roots,
Like
you're talking Myers-Berry now?
Yes, like shouldn't you have some 1 minus a squared or something?
Well, but to go to Boyer-Link, so this is in Boyer-Link's code. So this will give you the metric in. So this will be the metric in harmonic gauge. Then of course you have to rephrase it in Boyer-Link's code. I can quickly tell you what
For example,
happens.
something should happen at extremality, right? Or
So if n equals b, well, extremality for Myers-Berry, I mean.
is it
yeah.
not equal m, for example?
So for instance, you can put b equals 0 and put well, the extremality here is
Like
a square, but there is a different. So okay, you're asking about.
No, I'm just asking, like, usually in care, so
Yeah.
I'm used to think about care, you have the square roots m square minus a square.
Yeah.
So they just say that something strange happens when a goes to m, which is the extremal limit.
Okay, I have yeah, but this is of course different here.
Yes, but
So
it seems that if
extremality, so the mass parameter is related to, so the extremality condition is, so you have this redefined mass parameter, so I'm putting, so this gm times some power, some pi's and things. So this will be, this mu will be, extremality will be equal to a modulus a plus modulus b squared. This is the condition of
Yes.
extremality.
so if the whole thing is just quadratic in a, when a is equal to b, there is no, everything seems fine. I can just cross the extremality and nothing seems to happen.
Why do you cross extremality?
No, I'm just saying, if I would cross the, for example, if I look at the metric and if I would cross the extremality, I have like horizon, like
Yeah.
the square root.
But this is first order in G. So this
okay.
analysis doesn't know anything
All
about
these square roots are expanded out essentially.
But
It's
you
just-
only, yeah,
just-
that's
to
what I was
get
thinking.
the horizon to here you have to resum the
Yeah.
whole thing.
Yeah, but this is what I was confused because I thought that in the other case you have infinite correction in A and they should resum to the square root. But here it seems that the only correction you have is A square, so I cannot resum to any. But maybe you're saying that I should look at subbidding in G and.
Well, yeah, you have to resum in G to
Okay,
get all these
okay.
things. So so here you have two expansions. So in principle here you expand in A. Well, okay, you're not doing. I mean, well, this is not. Because
So you're
you can
expanding
do-
in G and
So of
in
course
A
you can't
and-
expand in
Yeah.
in A either. I mean, this is, but still you're expanding in angular momentum out of fixed order in G.
Okay, okay.
And then of course by the arguments I mentioned, you can in principle reconstruct all the from this three level analysis. You can reconstruct the whole metric.
Probably you can also see from the linear stress tensor of Kerr, the one on the right, the boxed equation, right? Boxed equation is resum in A.
Exactly, yes.
Yeah. And there's nothing happening there, I guess, for extremality, right? So I think the square roots that you have in mind are in the denominator, and here they don't show up until you resum in G, I think.
Okay, but we can see.
So let me quickly move to, well, I mean, there's just a few things I wanted to say. What happens for Myers-Berry itself? So Myers-Berry, okay, I'm not going to write down the for Myers-Berry, but if you take Myers-Berry in the way it is written down by Myers-Berry is basically what I would call Boyer-Lindquist sort of coordinates. So again, these coordinates are not ACMC. What we have to do is just the same analysis we have done in Kerr. So you expand, you write down your coordinates, say. So it's always a story. You write down your coordinates. So it will be something x1. It will be something like r sin theta cos phi 1. So you have in my sparing 5 dimensions, you have two azimuthal angle and one polar angle. Y1 will be r sin theta. So y1 and so on. So here x2 will be r cos theta. Cos phi 1, cos phi 2, and y1, y2. So these are the two planes of rotation. Cos theta, sin phi 2. Now you are in harmonic coordinates. So basically, these functions, these r and capital theta, will be functions of the r and theta of Myers-Berry. You plug this into the equation G mu, the mu of t x1, x2, x1, y1, x2, y2 equals 0, which is your harmonic condition, and you read these functions. From these functions, you get the metric in the new coordinates, and from the metric in the new coordinates, you simply read the multiples. And you can, and so the point is to get these objects here. So you get the multiples of Myers-Berry, and you want to read what these objects are. And we did it by brute force. I mean, up to level spin 7. We got some numbers, and then eventually, actually, Claudio Gambino realized that this was magically resumming in the following functions. So f2 of zeta is equal to minus 2 over 3. The Bessel function J2 of 3 over 2 zeta, F3 of zeta is 4 over 3 zeta, J1 of 3 over 3 zeta, and F1 of zeta is simply given by F2 of zeta plus F3. F3, so F2 of zeta plus F3 of zeta. So basically we get the full stress energy tensor for Myers-Berry as an expansion, so in terms of the angular momentum. In particular, the quadrupole terms are F2, 1, so the mass quadrupole, so you get from these relations you get the quadrupole, the mass quadrupole, and so the coefficient in front of the mass quadrupole and the coefficient in front of the stress quadrupole, which are given by minus 15 over 32, and F2 2 is minus 3 over 16. Okay, so this is, so the point is, now this is our, this was basically our starting point of our field analysis. Now it's going to do field differentiation. So the idea is how can we reproduce these numbers from scattering amplitudes, basically. So from, and now, so let me conclude by saying what we quickly saying what we find. We simplify, we don't manage to reproduce these numbers. But let me first mention, so what we do is consider first of all a vector, a mu in 5 dimensions. A vector is a representation 2, 2. So the polarization of this object is a polarization of massive vector is a 2, 2 representation of the SO4 group, which is the, say, the massive, say, little group. So what if the analysis, if I do the analysis in terms of polarizations as I did for the 4 dimensions, I should do 2, 2 tensor product with 2, 2. And I see that this analysis will produce a 3, 3 plus a 3, 1 plus 1, 3 plus a 1, 1. So you see that this is the mass, the single, single. This is the dipole. This is the mass quadrupole. And of course, there is no way in which these two representations, these representations will give me a stress quadrupole, which I remind you is the representation of phi 1 plus 1, 5. This representation simply cannot be obtained from the vector. So this representation will never get it. And if you work out this amplitude for a minimally coupled massive spin 1, you get an energy momentum tensor T mu, which is actually m u mu times 1 minus 1/4 zeta squared. So this is the coefficient f21 basically. Well, I'm sorry. This is the coefficient of the f2 plus the dipole term. We also consider an object B mu antisymmetric, a massive antisymmetric tensor, which is an object in representation. Well, typically we take a representation 3, 1 plus 1, 3. So this is reducing. And what we find in this case, so we just do the same group theory analysis, and we find in this case that you get indeed instead. You do not get actually this term, but you get a term T mu nu, which is m mu plus the dipole minus 1 over 2 m over 2 s dot q mu s dot q. So you get exactly this term. And this is where I'm gonna end. So basically, what this analysis shows that there is no spin universality in 5 dimensions. So according to the field I'm considering, I will get an expansion which can contain some multiples and does not contain others. So for instance, if I take a vector, simply there is a quadruple object structure that I simply cannot get. And so things become much more complicated. And well, it would be interesting to see. For instance, one idea that we have is to consider the limit in which J1 and J2 become very big, and see whether we can these terms will be modified to become more closer and closer to the values that we get here. Okay, so this is all I wanted to say. Okay, thank you.
Thank you. Questions? Everybody wants to go to the coffee.
Maybe I can ask something related to the thing that was previously. So here you're leading in G Newton.
Yeah.
And you're also expanding in spin. The spin of the black hole, for example. But that should, I mean, all orders in spin are leading in G Newton, right?
Yes.
Is correct. And the statement that you said before is that for Mears-Ferri, the whole series in spin is just two terms. Did I understand?
What did I say?
So you said that like so the sum in spin would be the sums over L.
Yeah, you are talking about the equivalent of this expression in for minus pairing.
I think so, but
So this expression for minus pairing will contain instead of this function this Bessel function. These Bessel functions here. By the way, we do the same analysis in dimension psi and phi. This is completely general. We have the expression of these objects in any dimension.
when you had this a minus b, a square minus b square, and then
This is 5 dimensions.
this
yeah,
dimension.
yeah.
So when a is equal to b, they will vanish except dipole and quadrupole.
That's true. Yeah.
So this was an expansion in, if you want, a square, and now the full infinite sum in a square is just two terms, just a plus a square.
No, but this is the full. Yeah, but the full. These are just all the multiples of the full solution.
Exactly. Yeah.
Because then the corrections in G will be simply less. Will be simply. I mean, the corrections in G will not change the multiples.
Okay, so the statement is that like
I mean,
at finite G Newton, the dependence in spin is just a simple polynomial, like a plus a square.
well, no. Well, I'm not saying. Well, I mean, not that you factorize this. I mean, what I'm saying is that the multiples are the objects I wrote down. But then when you start doing the corrections in G, the terms will mix up with the terms which are dropped, which will go to the less dominating, say, than the leading terms here. So you just simply get extra terms. I mean, it's just the R. So the equation will. I mean, the metric is source of the metric. So this is but this won't change the actual multiples.
Okay.
So, for instance, like Rexner-Nostrom. Rexner-Nostrom is an example. For Rexner-Nostrom, of course, has an energy momentum tensor, but this energy momentum tensor vanishes. It's good enough to allow me to still define the multiples.
Okay.
And what happens is that the terms proportional to the charge do not affect the multiple structure. So the multiple structure of Kerr-Newman is the same as Kerr, as far as gravity is concerned, because simply these terms go to infinity faster.
I understand now. Thanks.
Quicker.
Thanks.
Any further question or comment? Okay, if not, let's thank Fabio again.